Welcome to Chapter 3, the chapter on biopsychology. I'd like to share that this is my favorite chapter. In part, it's going to give all of us a greater understanding of the machinery that is our brain that allows us to think and feel and act. And it'll also give us a much greater understanding of not only standard thought and behavior, but also mental illness, anything from depression to Parkinson's. So let's begin. So let's see if you remember what biopsychology is back from Chapter 1. Back then we defined it as the area of psychology which studies the biological basis of. Take a moment and see if you remember. The mind, no, remember psychology began there, but its current focus is much broader. Was psychology always the study of? If you're thinking behavior, absolutely. If you're not, that's fine too. Just put into your mental checklist of behavior. Now, if you would for me, please consider some of these influences. What are some of these biological influences of our behavior? Take a moment and then compare what you think to the next slide. So let's see how you did. The first picture in the bottom represents the endocrine system, the hormone-making glands. Second picture, of course, the brain. Third picture, representing DNA, genes, and all influences that are hereditary. The next picture, a neuron, which is also the prominent picture on the slide. And the last picture, the chemicals of the neurons, the neurotransmitters. How did you do? So let's start with the endocrine system. Endocrine is just a fancy term for hormone. So instead of saying I'm going to a hormone doctor, you might say I'm seeing an endocrinologist. Hormones are chemicals made by these glands, and these chemicals are released directly into your blood supply so they could course through your body, of course including your brain. So we're going to start, if you would, draw a silhouette in your notes, and we're going to start at the head and work our way down, looking at most, but not all the glands. So let's start with the three that are located in the brain. Are you aware of any of the three? Well, let's start with the one called the hypothalamus. So draw a shape into the brain, if you will, and label the hypothalamus. The hypothalamus controls the pituitary, an extremely important job. Next in the brain, draw right next to it a little shape for the pituitary. And again, it does not have to reflect the shape shown on the right. Just draw a little circle, perhaps. The pituitary is sometimes called the master gland. Think of maybe the master cylinder of your car. The pituitary controls all the rest of the glands. So hypothalamus controls the pituitary, and the pituitary controls all the rest of the glands. So if you need to see an endocrinologist, maybe you're a guy with low T, maybe you're diabetic, maybe you're a woman with osteoporosis, the doctor would be checking on the functioning of three different glands: the hypothalamus, the pituitary, and the particular gland, because if any one of the three malfunctions, it will affect all three. And how do they check it? Well, sometimes it's by feeling it, such as a doctor might feel the gland in your neck. And they're also checked chemically, so they'll analyze the different hormones in your blood supply. So we have the hypothalamus and pituitary. Let's consider the last one in the brain. That would be the pineal. Now, the pineal gland plays a very important role in some body rhythms. We'll consider much more detail later on in the chapter when we get, or the course rather, when we get to the chapter on consciousness. So for right now, we've identified three in the brain: hypothalamus, pituitary, and pineal, and we note the basic functions of each, and for us, that's all we need to do. Let's move on next to the one in the neck. Do you know its name? So now let's consider the gland in the throat. Do you know which gland it would be? If you said thyroid, you're correct. We also have parathyroids there as well, but we won't consider them for our class. If you look at the shape of the thyroid, what does it remind you of? Some students say a butterfly or a bow tie. What if you're a Star Wars fan? Maybe a TIE fighter? But it has this particular shape. It's located in the throat, and that's a great mnemonic. T is for thyroid, T is for throat. The job of the thyroid is to regulate metabolism. Maybe you know somebody that says that, oh, I'm hypothyroid. Maybe you know somebody else that's hyperthyroid. They would have a distinct and profound effect on their metabolism. The thyroid needs a raw material in your diet to do its job effectively. Do you know what that raw material might be? Some students say sugar. No, that's a different gland. Some students say salt. Nope, that's yet a different gland. The thyroid needs iodine. So perhaps you buy iodized salt. Good enough. Let's move on. Let's move on to the abdomen. So far we've identified brain-related glands, one throat gland. The rest are down in the abdomen in different layers. Let's start with perhaps, if you draw in two kidney beans, these are your kidneys. They're not adrenals, but they're useful. So draw in the abdomen two kidneys and draw a gland on top of each kidney. Do you know what this gland would be? Well, it would be your adrenal glands. What hormones would the adrenal glands make? Quite a few, but there's just two that we'll associate with in this class. Adrenaline, that would make sense, and also the stress-related hormone cortisol, which we learned about before. As a mnemonic to help you remember where these particular glands are located, if you know the biological word for kidney, the fancy word for kidney, it's renal. So what would you call a gland that's been added onto your renals? You might call them your adrenals, hence the fancy name for the adrenal glands, a gland that's been added onto renals. So that way you'll never be the student that tells me, it's in the throat or it's in the brain, as long as you know where the kidneys are located. Next, let's consider a particularly big gland, the biggest of the endocrine glands, located in the abdomen, the pancreas. People that have a malfunctioning pancreas might have what serious disease? Diabetes, yes. And what are the major hormones, at least what is one major hormone of the pancreas? Insulin. So perhaps you know a diabetic that injects insulin, they have a defective pancreas. This will be the only point in the course we will talk about diabetes. Diabetes is associated with many profound and severe health conditions. Think for a moment and think about as many of these health conditions that are typically associated with diabetes. So unfortunately, diabetics are likely to have circulatory problems. If one has circulatory problems, of course relating to the functioning of the heart, how can that affect the body? Well, if the toes, the furthest part from the heart, don't get enough blood, they can actually die and become gangrenous. They can get gangrene and may have to be amputated. If it goes further, the person might lose the foot or even the entire leg. Other people with diabetes have terrible nerve pain. Other people have kidney issues. I had one colleague that was both diabetic from, the person had kidney issues as well as heart issues and had to go on dialysis. I had another colleague that had actually several toes amputated due to his diabetes and also went blind. So blindness is another severe complication. And this is just a short list. So it's important, if at all possible, to avoid the diabetic status. What can one do? Sometimes simple weight loss when a person is approaching diabetes, sometimes simple weight loss will make the difference between this and not being diabetic. Similarly to sleep apnea, sometimes a little bit of weight reduction can go a long way. Right now we're seeing an explosion in diabetes in this country, even in children, and that used to be so incredibly rare, but it's not rare anymore. Why are we seeing so much diabetes? Increased body weight, due to many factors including our fast food diet and lowered activity. So again, do everything that you can to avoid this diabetic status. And that will be our conclusion of our diabetes discussion. So in the abdomen we mentioned adrenals, we mentioned pancreas. Let's consider now the gonads. So the testicle, or testes in other words, of the male, and the ovaries of the female. Let's start with the testes. What are the major hormones of the testes? Testosterone, and there are many forms of it, including the dreaded dihydrotestosterone associated with male pattern baldness. But anyway, testosterone. Just as a little trivia, the word testify. Do you know the origin of the word testify? Well, in ancient Greece, men who were to testify would swear an oath, not on their heart, not on the Bible, the Quran, the Talmud, as you might be guessing. Yes, they swore an oath on the testes. Implication for lying, I think, would be very, very clear. A related question, could the women of ancient Greece testify? No, they were very third-class citizens and clearly could not testify. Putting your hands on somebody else's testy would not at all be the same thing. So no, they were not able to testify in court. Let's consider the ovaries. They make various hormones. We'll focus on two. What are the two most prominent ones? Estrogen and progesterone. Spelled for you on the right. Consider the word progesterone. You see gest in it. Can you think of any medical words with gest? Well, I'm particularly thinking of gestation. What does gestation mean? Or to gestate? Refers to pregnancy. So literally, this is the pro-pregnancy hormone. So if a woman's levels of progesterone were too low, she could not get pregnant, or she could not keep the pregnancy to term. Thank goodness we have artificial progesterone to help her. Another question, if a woman's on a birth control product, it's often a combination of estrogen and progesterone. Why? Well, if her levels of estrogen and progesterone are made artificially high, it psychs the body, I like that word, it psychs the body into thinking it's pregnant. And if her body thinks it's pregnant, she will not release an egg because the body already thinks it's pregnant. So it prevents egg release because it simulates pregnancy, and a lot of the side effects of many of the birth control hormonal products mimic pregnancy. So there you have it. You should be able to identify on a silhouette that you draw where the glands are located, a hormone associated with the gland, if we noted one, and any particular details. I hope you enjoyed learning about the endocrine system. I find that particularly interesting. In graduate school, I studied that particular topic as part of my qualifying exams for the PhD process. But now let's turn our focus to Charles Darwin. And it's some blanks for you, so read the slide and see if you know any of the blanks. He spent 5 years sailing on a particular ship. Do you know the name? If not, I'll give you a hint. A particular dog, a smaller dog used in hunting. And as a little bit of trivia, I volunteer for a rescue in Saratoga, a Hope Rescue, and I've adopted out so far 2 of these dogs this month, and I'm getting my 3rd one today, which I'm quite excited about, and I already know a home that is interested in this particular dog. But anyway, a small dog used in hunting. The Beagle. So he spent 5 years sailing on the HMS, in other words, Her Majesty's Service, Beagle. He studied variations in what particular species? Birds, yes. What type? Finches. Across the many islands of they're a chain off of South America, the Galapagos. And they were critical to his theory of evolution. If you need help spelling any of those, you'll see them on the next slide. Based on this, he wrote a world-changing book, a foundational book of science on the origin of species. Again, let's take a look at the next slide. So if you need any spelling help, like in the word Galapagos, which I would too, it's on the next slide for you. Now let's turn our focus to the very briefest introduction and coverage of the topic of genetics, starting with the father, one Gregor Mendel. Does anybody have an idea what species he used? A plant, yes. What particular plant? The pea plant. So you breed pea plants year after year after year to see how the transmission of traits happened. And he stumbled on a great choice because it has many characteristics controlled by dominant and recessive genes. So tall versus short plants, white blooms versus pink blooms, this color pod versus that color pod, smooth pea versus wrinkly pea. You get the idea. So he bred this plant year after year and learned the foundational concept of genetics, dominant and recessive traits. In other words, dominant and recessive characteristics. Would you know what he did for a living? You might be able to glean it from the picture. Many students say geneticist or biologist. No, that was his hobby, but a good guess nonetheless. Did the garb look a little bit religious? He was in fact a monk. So Gregor Mendel was a monk. Now he knew he was onto something very big. So after he did many, many years of research, he presented it before a board of learned men. They should have been wowed. If the Nobel Prize existed back then, he should have gotten it. But they were thoroughly unimpressed. Why? They critiqued his work as not being mystical enough. So apparently they were not fans of the scientific method whatsoever. They wanted mysticism. And he had serious science, which was apparently not to their liking. But even though he did not get credit in his lifetime, he has certainly credit in our lifetimes. So what are those structures shown at the bottom of the page? If you're thinking chromosomes, definitely. And you can see that they've been organized, because scientists are very organized typically, into pairs. How many chromosomes will we find in a normal human body cell? For example, a cell in your nose or a cell in your toes. If you're thinking 23 of these chromosomes per cell, you are wrong. 46. Now if you said 23 pairs, fine, but 23, unless you add the word pair, is not the same as 46. So a cell in our nose, a cell in our toes, and those cells in between would have either 23 pairs or 46 chromosomes. Now let's go to the next slide. You'll see something kind of interesting going on in the next slide. So consider this karyotype showing the human chromosomes. You can see each chromosome looks like the member of the other pair. Yes, sometimes they're bent, but if your arm is straight or bent, it's still your same arm. But look at the bottom right. That pair is very interesting. One is much bigger than the other, a significant mismatch. What term would be used for this person who possesses this mismatched chromosome? I will say that I do have such an individual in my family. You could possibly have an individual like this in your family. What term would we use? Some students say Down syndrome, and I'll say not necessarily intellectually disabled. Sometimes I hear autistic, not necessarily on the spectrum. A dwarf, not necessarily size challenged. And once in a while, students will volunteer the correct answer. Male. So dude, guy, him, yes, this is the male pattern for the 23rd pair of chromosomes. And I do have two such individuals in my family. I have my father and brother. So this would be the male pattern. And again, this is specific to the 23rd pair of chromosomes, our sex chromosomes. What pattern would we find for the 23rd pair? We would use the term XX. What would we term the pattern for the male pair? XY. And I realize it doesn't look like an X and doesn't look like a Y, but is in terms of letters indicating the unknown, because for a while we didn't know what these chromosomes do. So again, the pattern you see is the XY chromosome for the 23rd pair, the female pattern, the XX pattern for the 23rd pair. You might also see something else interesting. If you also look at the bottom row, you'll see in one particular chromosomal pair, there's 3. What do we call this person? That would be Down syndrome. And we will talk about Down syndrome later in the course. That's when a person has an extra chromosome, a trisomy. And with that, for the moment, we are done with this particular topic. Now let's consider the divisions of the nervous system, central and peripheral. On the next slide, we'll see the breakdown of these two branches. So let us begin our discussion of the nervous system, starting with central nervous system, often abbreviated CNS. The two parts of the CNS are encased in bone. They are surrounded by bone. So that would be our brain and our spinal cord. Now the other big branch is the peripheral nervous system, like the word on periphery, meaning outskirts or outside, because it's outside of bone. So the two big branches are somatic and autonomic. Let's start with the somatic. I would like to train you so when you look at the word somatic, you see the word soma, because we'll use the term soma a few different times in this course. Whenever you see soma, translate that to yourself as meaning body. So literally, it's a branch having to do with the body. So soma means body. Let's get more specific. These are the wiring. In other words, these are the nerves that allow us to move our body and feel our body. So if you look at these diagrams of the people, you'll see nerves running down the arms, the legs, and so on. These are somatic nerves, the wiring that allows you to move your body and feel your body. So for example, maybe you don't own a proper bagel cutting device, or maybe use an improper bagel cutting technique and slice your hand and see the doctor might be very concerned that you might have severed a somatic nerve. If so, you would not be able to move your fingers, or it's possible that you could move your fingers but could not feel your fingers. So what does soma mean? In this case, the nerves that allow us to move our body and feel our body. Okay, let's look at the other branch, autonomic, not automatic, though it is. The word is autonomic. Its job? To control your organs and glands. It has two divisions, sympathetic and parasympathetic. Sympathetic is our stress-related branch, our emergency-related branch that we spoke about in our earlier chapter on health. And remember, as a mnemonic, if you're a nice person, you'll feel great sympathy if somebody's all stressed out and having an emergency, so you should easily be able to link sympathetic and stress and emergency. And we looked at many of these effects, speeding up the heart rate, speeding up respiration, dilating pupils, releasing sugar into the blood, and so on. The parasympathetic, the opposite. When you're resting, when you're relaxing, maybe when you fall asleep at the end of the movie before you see its conclusion. In this one, certain activities are enhanced, such as digestion, but this is for the maintenance and overall just regular running of the body. So study this until you're comfortable with it. Here's just another portrayal of the divisions of the nervous system. This one, though, does like to highlight the sensory and motor pathways, but in every other way, it's same as before. Here's a little review activity. I hope that you're just not going through these PowerPoints from beginning to end without stopping. You need to learn it as you go along. So here's a nice activity to see if, after you've studied, if your learning is sufficient. Reading is not sufficient to do well. You've got to test yourself at every step. Something can seem familiar if you look at it, but it's only useful if you've learned it. And to determine if you've learned it, you've got to test yourself. So please do take this opportunity to test yourself and create your own tests for every step and every PowerPoint as you go along for all your courses. And here's another review activity for you to do on your own. When you're done, of course, go back and check the answers, and any ones that give you difficulty, spend a moment or two or three studying it until you're comfortable, and then go on to our next material. Don't get nervous if you see a particular slide with no narration. Sometimes the slide is complete in and of itself. Now let's consider the two major types of cells found in our brain, the neurons, which we'll spend a lot of time on, and the glial cells, which we'll spend a very short amount of time on. On the next slide, we'll consider the basic parts of the neuron, but before that, let's look at the three basic neuron types. Let's start with motor neurons. What do you think motor means in this context? If you're thinking movement, exactly correct. So they allow us, they go to the muscles, they allow us to move our bodies. What about sensory neurons? They would be embedded in our senses. Can you give me some examples where they would be embedded in our body? Well, there are sensory neurons. If you're thinking your eye, absolutely. In your ear, absolutely. On your tongue, absolutely. Your nose, absolutely. And even in your skin. So they allow us to perceive the world and to feel our body. But the most common type of neuron by far is not our motor or sensory neuron. It is the interneuron. Think of them as a middleman of neurons, passing information between other neurons. Again, they are the most common. And with that, we are ready to move on to our next slide. For the next slide, please take the structure and draw it into your notes, and then we'll label it as we go along and note the function of each structure. Let's discuss a more recently discovered neuron, that is, if you consider the 1980s to be recently, called the mirror neuron. Let's pretend that you watch somebody maybe sipping a cup of coffee or soda. Neurons in the brain are firing as they do that. Well, some of the corresponding neurons in your brain fire as you watch them do it, so you can understand the experience. You can relate to the experience. The neurons that are firing in your brain as you watch are the mirror neurons, or considering watching somebody yawn, you'll often yawn yourself, again, because of the mirror neurons. It appears that in some people on the spectrum, there are deficiencies in their mirror neuron. So people on the severe end of the spectrum might watch somebody do a behavior and there's no corresponding neuron activity in their brain. So for some people, it might be part of the autism puzzle. So if I was teaching in front of you, I would draw a basic neuron in, maybe 20 seconds, and it will be quite functional. So let's start with those branching tree-like structures coming off the main body, shown in yellow. Do you know their name? If you're thinking dendrites, correct. So those branching tree-like structures are the dendrites. If you're up on your Latin, dendrite refers to tree, because don't they look like the branches of a tree, or maybe trees themselves? They're often called dendritic trees. For each structure, you need to note its function. The function of the dendrite is to receive messages, or if you want, you can put receive chemicals from other neurons, and then deliver it to the cell body. So again, receive chemicals or receive messages and deliver to the cell body. So the cell body would be that bulk of that structure shown in yellow, not the gray thing inside, that's the nucleus. So the center from which all the dendrites protrude, that center, that is the soma. And remember we learned the term soma before, and we said soma is body. So our fancy term for cell body is the soma. Next, you'll see one long cable-like extension. Do you know the name of that? Axon. Axon carries, you can say, the message, or you can say electricity. So it carries information away from the soma. And I chose that phrasing as a mnemonic. So dendrites deliver, axons away. That way, if you learn it that way, you'll never confuse it on a test. So again, dendrites deliver, axons away. Now you see wrapped around the axon, there's this little bit of pink insulation. Do you know the name? Well, if you're feeling fancy, myelin sheath. If you're not feeling fancy, myelin. But let's go with myelin sheath because it'll help us remember something very important shortly. So this myelin sheath is an insulation. It's made of lipid, in other words, fat. Fat is a great insulator. Think of whales and porpoises in the Arctic. It's necessary to insulate this axon. Just like in your house, if you had bare wires, uninsulated, it could be big and bad. Well, in your nervous system, if you have bare axons, uninsulated, it could also be big and bad. Do you know the name of the condition a person has? A very serious condition in which they have issues in insulation? Think about that for a moment. Cerebral palsy? No. Alzheimer's? No. Multiple sclerosis. And as a great mnemonic, if you have damaged MS, in other words, myelin sheath, you can get MS, in other words, multiple sclerosis. When I began teaching, I would ask my students, does anybody know anybody that has MS? In the typical semester, not one student would raise their hand. Often in the typical year, no one would raise their hands. And if I was teaching in front of you, I would have students raise their hand, and sometimes as many as half of a class, or sometimes even more, will raise their hands to say that they know somebody with MS. So we're seeing an explosion of MS in our culture, rather like an explosion of other things, such as individuals on this spectrum or other issues. I suspect that they're related to maybe chemical changes on people's bodies, related to problems in our environment. But in any case, what are some of the major symptoms of MS? Let's discuss it briefly. So a person has trouble controlling voluntary movements. So maybe deciding to stand up, deciding to reach out for something, deciding to walk. And it can come and go where you might see them with a cane and a wheelchair, and they may be walking freely, but it does progress typically to the point of lethality after so many years. They might have trouble also with seeing, sometimes with thinking clearly. And unfortunately, it can be a very painful condition. So again, associate MS with MS. Now at the end of the axon, you'll see some branching. And if you could, if you're drawing this in your notes, which I hope you are, draw little circles like little buttons. It's not shown in this particular slide, but draw them in, again, at the tips of these little branches at the end of the axon. These are called synaptic boutons, or in other words, synaptic knobs. For their function of these synaptic knobs, contain chemical or stores chemicals. This is where the neuron stores its chemicals. Next, you'll see that I drew a space between the end of one axon and the dendrites of the other two smaller ones. In that space in there, between these cells, put the word synapse, because that's what a synapse is. That's our last term. Synapse is a microscopic space between neurons. So when one neurotransmitter releases its chemicals from the knobs, it crosses into the space, and it would interact with the dendrites of the next cells. So there you go. So make sure that you could draw and label this if asked on a test, because I have often put a drawing question. In fact, I always, up to this point, have put a drawing question on each test one. Sometimes drawing a silhouette of the human body and labeling the glands, sometimes drawing a neuron and labeling the parts. So let's build upon the previous slide. We need to talk about excitation and inhibition. Both occur when the neurons, something receives chemicals from other neurons. What structure? Dendrites. These chemicals can have one of two effects, and only one of two effects, on the neuron. We'll start with a simple process first. Inhibition. In inhibition, those chemicals cause that neuron to be less likely to communicate. So the dendrites of the neuron receive the chemicals, and now that neuron, that entire structure, is less likely to communicate with other neurons. End of story. Let's move on, if that's okay, to the more complicated process, excitation. So let's say that those dendrites are now receiving excitatory chemicals, causing the neuron to get excited. What this means is that the cell is now more likely to communicate. So inhibition, less likely. Excitation, more likely. Rather like people. If, let's say, two people are talking in the back of the classroom too much, the teacher will try to inhibit them, so therefore they will be less likely to communicate with themselves. And if you're excited, don't you want to communicate? Don't you want to call a friend, text a friend, walk over to them and share the news? So neurons are like people. Inhibited, less likely to communicate. Excited, more likely. Now, if a neuron is very excited, a process will begin. That process mentioned in the previous slide, the process is called an action potential. So at this point, we know what the parts are and how they work, but let's see how the neuron functions as a whole. So we need to learn something called the action potential. In this process, electricity will be made. It will travel down the length of some structure, resulting in the release of something from the neuron something, take a moment and see if you can figure out, if we were working in class, we'd be doing this as a group. So the electricity would have to travel down the length of the axon. That could result in the release of, you can put chemicals, or if you're feeling fancy, neurotransmitters from the neurons' synaptic boutons, or if you prefer, synaptic knobs. So you have a description of the action potential in your notes, but it's possible that you're feeling a little bit fuzzy and unclear about it. And that's understandable. It's one of the more difficult concepts of intro psych. So please go to the following website and you'll see a visual of the action potential process. But this slide also helps to recap it. Please do both though. So you can see this slide that the action potential is now traveling down the end of one particular knob. You can see that knob is releasing chemicals called neurotransmitters into the space we identified as the synapse. The chemicals will interact with the dendrite of nearby neurons. Those chemicals might inhibit the neuron, or those chemicals might excite the neuron. If it inhibits the neuron, the process stops there. Conversely, if it excites the neuron and excites it excessively, it might have an action potential and could go from neuron to neuron through thousands of neurons in less than a second. Or again, if any one gets inhibited along the way by that same chemical, or the chemical being released, the process would stop at that point. Now, here's why it's important that we understand this. Every thought that you have ever had, every memory, every emotion, every movement, every behavior comes down to this process occurring and occurring correctly. Physical disorders, such as MS, psychological disorders, such as depression or schizophrenia, occur when there are difficulties or abnormalities in this process. So this process is fundamental to our existence, our health, and our happiness. So I think it's really important that we have a basic understanding of it. And now you do. I hope you found the previous slide amusing. It's hard to find action potential humor. That's from the Big Bang, which I actually started listening to after I used it in the learning chapter for this course. So we mentioned that chemicals are stored, chemicals are released, but now it's time to get into detail and learn about them and be fancy. The proper terms for these chemicals would be the neurotransmitters. We'll look at the basic intro psychology list, and for most of them, we'll associate that chemical with one or two health conditions. Literally, each chemical has thousands of effects, but again, I'm just pulling out one or two that affect our health. A different teacher might focus on a different function. Let's start our discussion of neurotransmitters with dopamine. Many teachers might relate dopamine to feelings of pleasure, whether it's natural pleasure or chemically induced pleasure, such as cocaine or amphetamine use. And this is true and also important, but let's focus on schizophrenia. People that have schizophrenia have an imbalance of dopamine in their brains. They have an improper quantity. If a person with schizophrenia is taking the medication, it tries to adjust the dopamine level of the brain to make it appropriate, and the person's symptoms typically disappear. We'll talk about schizophrenia in great detail later on in the course, so for now, let's say that it's perhaps the severest of all mental disorders, and it's associated with improper levels of dopamine, with more to come. Now with Parkinson's, this will be the only point in the course we talk about Parkinson's, so let's learn what we can right now. With people with Parkinson's, for unknown reasons, there's a small area of the brain called a nucleus, and in this nucleus, almost all the cells die, and these were dopamine-making neurons. So virtually all the famous symptoms come from the death of these neurons, so the loss of these particular dopamine neurons. What are some of the famous people, perhaps, suffering from Parkinson's? Maybe you're thinking of Michael J. Fox, or perhaps the famous athlete Muhammad Ali. Both of them were Parkinson's sufferers, and Michael J. Fox still is. What are some of the most famous symptoms of Parkinson's? That tremor? Absolutely. But if it was just a tremor, it would be an annoyance, but obviously this disease is far more than annoyance. This person will lose the ability to control their body, to decide to stand, to walk, to reach out and take a glass. And they'll also lose reflexes such as swallowing. What happens when you can no longer swallow? If you're in a poor culture, you might starve to death. In our culture, you would have a port put into your stomach to be fed directly. And as you've seen from the TV commercials, more than half of people with Parkinson's developed a dementia that looks very, very much like Alzheimer's. So again, associate schizophrenia and Parkinson's with the levels of dopamine in the brain. Next, let's move on to serotonin. And we'll do at the same time norepinephrine, a 2-for-1 situation. It should make your life a little bit easier. The second quote is not as iconic as his more famous float like a butterfly, sting like a bee, but obviously much more powerful. Made during the Vietnam War. He was jailed for refusing to go to Vietnam for a fight, and this quote came from it. Muhammad Ali can be considered to be an early Black Lives Matter activist long before that term was first used. Black soldiers were 23% of combat troops during Vietnam, but African American people at that time only comprised 11% of the population, so were overrepresented by twice their population number. So let's look at the commonality between the neurotransmitters known as serotonin and norepinephrine. They're related to mood and mood disorders. So individuals with major depression have too low of levels of these particular neurotransmitters. Medications that work on depression are thought to adjust these levels to appropriate higher levels and reduce the symptoms of depression. So again, associate these with mood, and we'll talk much more about major depression and other mood disorders later on in the course. So we know with Parkinson's, it's related to cell death starting in one specific small area in the brain. Alzheimer's, similarly, is also related to cell death, but this time it's massively and globally throughout the brain. And these cells that are dying are the acetylcholine-making neurons. And let's mention Alzheimer's in a little bit more detail, since this is the only point in the course we'll talk about it. It might have surprised you on the first day of the class to learn that Alzheimer's is a treatable condition. The next slide, we'll look at the 5 major types of drugs that are approved by the FDA to treat Alzheimer's. But what do we know about Alzheimer's? What's the first symptom? Typically, forgetting, usually little things. Where did I put my keys? Where did I put my cell phone? Did you misplace these this week? Often if I ask students, so I'll get 4, 5, 6 people that raise their hands, and sometimes I will too. This does not mean you'll have Alzheimer's. It starts as small things, but it'll become global and bigger until what do I do in a bathroom? How do I get home from the front yard? What do I do with a fork? Who are you? Might be their husband or wife or partner of 20, 30, 40 years. So it begins with small forgetting, getting to the point where the person cannot think. So memory is first initial symptom for many people, but they will lose their ability to think. Many people also have profound personality change. Sometimes personality change for either Parkinson's or Alzheimer's might be the first symptoms. So again, it will advance to the loss of the ability to think. Let's consider the next slide, which shows some of the major treatments, the 5 major classes. I won't narrate it because I just want you to show you that there are treatments. That's the only thing that you need to walk away from with the next slide, is just that there are treatments out there. And I would like you to know the time period that they first began. I remember where I was teaching when the first treatment came out. It was a very big deal. I was a new teacher at Jefferson Community College in Watertown. Just a little bit of sharing. On the first day of class, were you surprised to learn that Alzheimer's is a treatable condition? Certainly not curable. We're nowhere near close. We are learning amazing new things about it. But at this point, there are medications that are approved that will significantly slow the progress. At this point, early diagnosis and treatment can result in about 3 more years of high quality living, and 3 years can be a lot. So that's where we are right now at the time of this recording. The last drug on the list was approved in 2021. Very different than all the other drugs, actually addresses the issues at the level of the brain, versus other drugs are just used to improve functioning in terms of memory or cognition. It does represent a tremendous step forward, but at the same time, reports about it are frankly disappointing. But another tool in our arsenal is great, even if it's not a great tool. Next, let's consider GABA. You might say, thank goodness one has a short name. Not really. Its name is so long that we rarely say it even full length and try to avoid writing it full length. Gamma-aminobutyric acid, so you can see why we're just going to call it GABA. It is the major inhibitory chemical of the brain, so when it's released, it just about always inhibits the other neurons, making them less likely to have an action potential. We'll relate it to alcohol use and epilepsy. So let's start with alcohol use. Alcohol is inhibitory, so yes, it might make you feel nice. Maybe people might act uncontrollably, but it is inhibiting cells, maybe inhibiting the neurons involved in reasoning and judgment, so the higher brain functions. So people may say things they might not normally say. They may do things they may not normally do because alcohol has released them of their inhibitions. It is inhibitory. And if you have too much of it, it will inhibit the lungs and the heart and other vital organs to the point that you might actually die. So again, it is a depressant. It is inhibitory. We'll visit alcohol later on the course. Let's consider epilepsy in terms of what it is and how it relates to neuron firing. So let's please go to our next slide. So let's consider epilepsy. It's very common that I'll have an epileptic student in a class who will share some personal information, and it's also always greatly appreciated. In an epileptic seizure, what happens is that the neurons in your brain, instead of firing in carefully or having those action potentials in carefully, purposely planned out fashions, the action potentials become random and chaotic. Think of maybe an orchestra playing to the same music. That's a normal brain, versus an orchestra that's tuning up, making all sorts of noise, not doing anything in coordination. That tuning up is rather like the seizure, without purpose, without plan. When a person goes into the seizure, they could have, depending on their form, a petit mal seizure or a grand mal seizure. Let's consider these two terms. What does petit or petite mean? Small, M-A-L, bad. So literally translates as a small, bad type of epilepsy or seizure. A person could be sitting right next to you and have a petit mal seizure, and you might not know it. I could look right into their eyes as I teach, and I might not know it. And when they come out of it, they might not know it. Have you ever had a teacher do a whole lecture, 5-10 minutes, and a student asks, aren't you going to cover something? And the entire class laughs and wonder, where have you been? Well, maybe texting under the desk is a possibility nowadays. But if that's not the case, they could have been in a petit mal seizure. So looking normal, but not processing information. Now, sometimes if you're not processing, it's obvious. If you're driving and you stop processing, in a few seconds, it will be sadly obvious. If you're, say, riding your bicycle and start processing, your legs will stop and over you'll go, it will become obvious. But just sitting in classroom or watching TV, it might not be at all obvious that a person had a petit mal seizure. Petit mal seizures in epilepsy are often outgrown Many children will get them less and less commonly until they disappear altogether. That's often, though not always, the case. Let's consider a person with a grand mal epilepsy or seizure. Grand, big or large, so literally big and bad. This one you will not miss. The person will lose consciousness and convulse. Now, let's say this happens to you and you're the only person there. What should you do or not do? And you're probably thinking, what are the chances this will happen to me? Well, it happened to me twice, so it's quite possible. So let's consider what we should do if we're the only person on a scene and somebody is having a seizure. So if I was teaching in a traditional manner right now, I'd ask the students to volunteer, what things do you hear that we should do, or what things do you hear that we should not do if a person has an epileptic seizure? The following slide is a list of common things students tell me to do or not do. So let's take a look and see which they fall into, the do or please, 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 please do not do category. So first one on the list, time it. You can never go wrong. Write it down, perhaps on your hand, so you can tell the EMT should you have to call one. Doctors will need to know how long the seizure lasts. Next, call 911, but believe it or not, you do not have to call them instantly. According to the American Epilepsy Foundation, they suggest you wait as long as 3 minutes. In all honesty, I chicken out at 2 minutes. Many students say put something in the mouth. And according to the American Epilepsy Foundation, stay out of the mouth. People have had their teeth broken by people trying to pry in. They have had objects put in their mouth which they have bit and broken teeth on. They have ripped their skin on the side of their mouth from these objects. They have choked on these objects. So unless you are a medical person trained with the proper device, stay out of their mouth. Is a guidance that will serve you well in life. Unless you're invited into somebody's mouth, you've got no business being there. So stay out of the mouth. Next one, roll on side. Why? It's called the rescue position. Some people are very concerned that humans will swallow their tongues. Not possible. Our tongues are not long enough. If you peek at the next slide, you'll see that even those two individuals with amazingly long tongues, they cannot swallow their tongue. What can happen, though, is the tongue can rest back and block the airway. If you roll them on the side, the tongue rolls free, and now you've got a good airway. Also, sometimes people get frothy when they're having a seizure, and I've seen that personally. Again, roll on side. It's considered the rescue position, useful really in any condition in which a person is unconscious as long as there's not a spinal injury. So roll them on their side. Don't restrain. The person's not going to get up and run away. But people have had all sorts of injuries from broken wrists and ankles from being restrained. Don't restrain. I would not be opposed to slipping something underneath the head for padding, though many people have had neck injuries from people lifting the head too vigorously. So if you look at number 11, it says padding under the head, only if you don't lift the head. And again, the American Epilepsy Foundation would caution you against this. So I would say be very, very careful, to say the least, if you go to this direction, and don't restrain the head. Next, don't use CPR if the person's breathing normally. CPR to me is like a formal gown or maybe tuxedo. So few cases and circumstances to use it. We want to use it. Don't use it. So if you saw the movie Son-in-Law with Pauly Shore, very fun, stupid movie, don't give CPR if it's not needed. Why? Well, even great CPR often results in broken ribs. They don't need or want broken ribs. Next, check for medical ID, a necklace, a bracelet. It might tell you instructions. Take right hand, place on chest. I'll get back to you in a moment. That's better. Later on, we'll learn about the technology, which they may have implanted in their body. But for now, look for medical ID and do what it says. Next, loosen tie or upper buttons if it seems to be restricting their airflow. Next, when they come out of it, they're going to be very confused. I remember one circumstance, the young lady was having a seizure in the hallway in between classes, and I stayed with her until she came out of it. And when she came out of it, she kept asking, why am I laying here? Why am I laying here? And I kept saying, well, you just had a seizure. You're just fine. But we called the EMT, so let's wait here until they show up, things to that effect. And for the next 10 minutes or so until the EMT showed up, she kept asking that question because she was so confused. What if she tried to cross the road in front of the college? I've seen 2 different people hit there. It's dangerous. Please use the tunnel. What if she tried to drive? Again, she would have had an accident. So reassure them, and if you could possibly persuade them to stay put until they're clear or until an EMT arrives, please do so. You can't forcibly restrain them, but try to convince them. Next on the list, don't give them food or drink. Why? What if they go into a seizure again? They could choke. So no food or drink necessary. Patting on the head, we mentioned that. Be careful. Number 12, protect from hazards, protect from harm. So if there's move the table and chairs away from them. If there's a coffee cup above their head, well, move it. Protect them from harm. I also say protect them from well-meaning idiots, and I share the story. Yes, I did say idiot. Back years ago, there was a local gentleman that used to go to health classes and talk about his epilepsy. He was difficult to understand. He had a speech impediment, which he acquired during a seizure. He was a construction worker. He had a seizure at a job site. His colleagues, not being the most learned of men, were very concerned he would swallow his tongue. Not possible. But anyway, they took the implements of their trade and made sure that he did not swallow his tongue. Any guesses? Think really idiotic. They took a nail and a hammer and nailed, going under his chin, they nailed his tongue to the roof of his mouth. Yes, I did not make that up. Yes, he caused a lot of damage. It's lucky they didn't kill him. If he got a major vein in the tongue, he could have bled to death. But in any case, protect them from well-meaning idiots. I did have a student share that she came out of a seizure one time, soaking wet with cold water. They doused her, trying to help her. She was not appreciative. So the net end effect of these 2 stories is, please protect this person from harm. So to do or not to do, we have some now basic ideas. So why were we talking about epilepsy? We were tying it to the major inhibitory neurotransmitter. So when a person has an epileptic seizure, they don't have enough inhibition in their brain, so the neurons get out of control, wildly having action potentials. So again, GABA is inhibitory. So if you have a neurotransmitter that almost always inhibits, it would make sense that we have another one that almost always excites, that is, causes action potentials. So glutamate is our major excitatory chemical. We'll relate it to the health condition of the DTs. The DTs are potentially lethal. They're potentially fatal withdrawal symptoms related to one highly specific drug family. Do you know the drug? If you're thinking of the heroin/poppy family, nope, it is not related to those. You cannot get the DT from heroin or poppy plants. So it would be alcohol and alcohol-identical drugs like the barbiturates, and that is the correct spelling, by the way, and the benzodiazepines. So alcohol-related drugs. So, if you want to know what the DTs stand for, delirium tremens, and no, you don't need to know that, just we'll call it the DTs. So let's say the person's used to drinking a lot of alcohol. They're an alcoholic, and in the severe end of being an alcoholic, and they, for whatever reason, don't have any alcohol in their brain. So they don't have enough of the inhibitory chemical. So if they have too little GABA, too little inhibition, their brain becomes overly excited. So the DTs can begin. So first they'll start to feel like they have the flu, or maybe like they're coming down with COVID. They'll feel bad. They might start to shake. They'll probably feel nauseous. Then their heart might start to race, and they might start to go in seizure after seizure after seizure, and they can die in the DTs. So that's why alcoholics might go to a detox facility so they can be carefully taken out of this condition, because going cold turkey, whether it's they decide to quit cold turkey, maybe there's a flood and they can't get to a liquor store, whatever reason, if a brain that's used to swimming in alcohol has no alcohol, the DTs can happen and they can be fatal. So let's consider our last neurotransmitter. Let's now consider endorphins, the last on our list. I believe this is the one that students enjoy talking about the most. Its normal functions, do you have any idea? Well, the primary one is pain control. A secondary one is pleasure. I used to minimize the pleasure one, but I recently read a study in which they developed a new drug against eating disorders. And it went through the first phase of testing with people very nicely. People lost a lot of weight. It was very effective. But in phase 2, they found a scary number of people committed or attempted suicide. Apparently, the drug interrupted their ability to feel pleasure. So although it was initially effective, it obviously was not approved. So my point is that although its key function is to help us cope with pain, the pleasure functions are important also. What are the drugs or the substances that affect this? It would be the opioid family. You can say either opioid or opiate. What would be these drugs? Certainly opium. From that was synthesized heroin. Also drugs like codeine for cough, morphine for pain, and many, many other drugs as well. Now these drugs reduce pain and make most people feel very good, though many people do not like the effect either. But in any case, for most people, they cause pleasure. What are some non-drug ways, without self-harm, that we can cause endorphin release? So many ways. Students will often say exercise. Great answer. But I usually say, we're all dressed up for work and school. We don't want to get sweaty. Give me some non-sweaty ways. Well, it can include laughing. It can include listening to music, particularly music that you really like, but listening to music. It can be spicy food, though very spicy food will cause you to sweat. It can also be a cold shower, that's for pain, or a hot shower. It can be a massage. Somebody always suggests sex, but I said, well, sex is a sweaty endeavor, and gets a laugh. So anyway, so there are many ways to cause endorphin release, and these ways are healthy. And now we have now concluded our basic coverage of neurotransmitters. For as you study, make sure for each one that you can list associated conditions and maybe an overall definition, such as for GABA or glutamate. The next slide is also a review slide. See if you can do that from memory. So before we go on, let's just assess our studying. So take a moment and see if you can label the different structures and identify what each structure does. So again, now since it's plowing through the PowerPoints one after the other, check your studying for accuracy and weaknesses as you go along. You'll find it much more effective and you'll be much happier with your tests. Plasticity is the brain's ability to change after learning or after brain damage. At this point in the class, I ask if anybody knows anybody that's had a stroke and what did they lose and were they able to recover. In general, younger brains have much greater plasticity. So 3 people with the same brain injury, say a baby, a 12-year-old, and a 58-year-old, the 58-year-old might have some trouble or significant trouble. The younger person, less trouble, and the baby may show no permanent change whatsoever. So plasticity is a very desirable trait. So as you learned from the previous slide, with no narration, that the other major player in the brain, cell-wise, is the glial cell. You actually have far more glial cells than you have neurons. There are different types of glial cells with different functions. We're just going to look at one, the most interesting, I think. It would be a reasonable conclusion that a neuron makes its own myelin sheath, but actually, myelin is made by glial cells and provided to the neuron's axon by these cells. So what disease should we associate with problems of glial cells? MS, so multiple sclerosis, is actually due to malfunctioning glial cells. Very interesting, yes? Let's now begin our consideration of the brain, what many scientists have called 3 pounds of electrified jelly. The structures of our brain can be placed into one of 3 divisions, that of hindbrain, midbrain, and forebrain. If you take an N in Phys, you'll have to know which structure goes into which division, but for us, as long as you know the 3 basic divisions, you're good to go. If we were in a traditional classroom right now, I would pass around the brain model for people to take a look at and feel. It would have 2 balls at the base and a stem. You could feel the cracks, the sulci, and the outer part, the gyri. You would notice that it's very hard, which is not like a living brain. A living brain's like butter on a 90-degree day sitting on the countertop, very soft. For our convenience, we divide into 4 regions. Do you know what the term used for each of those 4 regions? One word. Lobes. Does that remind you of a surgical procedure? Perhaps the lobotomy, which is no longer done. The term cortex means bark in Latin because it's rather like a bark, an outer surface, an outer covering. So let's continue and learn about the 4 lobes of our cerebral cortex. Let's start at the rear with the occipital lobe. Do you know what this is for? It processes visual information. So for example, the man who mistook his wife for a hat had a tumor in his occipital lobe, so his eyes would send the information for processing, but the lobe was not up to it. Hence, he had unusual behaviors, including patting fire hydrants because he thought they were children's heads. So to see, you must have a functional occipital lobe. Next, let's consider the parietal lobe, which has a special cortex called the somatosensory cortex. So the word soma, the word to, and then sensory. So somatosensory. This gives us our 3 body senses. What do I mean by body senses? Not all our senses, but those 3 sensory abilities found over the entire surface of your body. Can you think of them? Some people say smell. No, you could be smelly, but your elbow cannot smell other people. So it wouldn't be smell or taste. So it'd be touch, temperature, and pain, the 3 somatosensory senses. Just add the word somatosensory to the PowerPoint to help you out. So parietal lobe, the 3 somatic senses. Now let's consider the lobe shown in yellow. Please excuse Cooper, my new rescue dog. He's a foster dog who has already found his new home and is being picked up tomorrow, the lucky little doggy. He's a beagle. So temporal lobe, if you look closely at the word temporal, it'll tell you its location and function if you know how to read that word. So let's indeed learn how to read that word. So what words do you see as you look at the word temporal? A lot of students say temp, but temp is not a word. It's a shorthand abbreviation for the word temporary. So that would not be it. So tempo, yes, that would be. And oral, that's another word. So we hear tempos, letting you know one of the major functions, hearing. Oral as in speech, oral as in language. So we hear words. So hearing, and think of it as a language center, a speech center. In terms of location, well, since we hear with our ears, that's where the ear would be on the head. So it tells you location and the 2 major functions if you know how to read the word temporal properly. And now you do. Now let's consider the frontal lobe, saving the best for last. It too has a language center, at least the left side, same as for the temporal lobe. We'll learn momentarily from the Phineas Gage information that personality is strongly associated with the frontal lobe, hence the old frontal lobotomy, which we no longer do. Also, I don't know if you want to call it social skills or social planning, but definitely. There's also motor cortex here, the control of movement. Also planning, whether it's your day, your schedule, or your life. So planning, so you can see many important functions. So most semesters I have students do a drawing, either maybe I provide the offhand the silhouette and have them label the lobes and identify them. Sometimes they draw a neuron. Sometimes they draw a silhouette and label the glands. Make sure that you can do these 3 tasks. But for now, let's go to the slide on Phineas Gage. You're going to find this very interesting, I think. Please use the link and learn about the experience of Phineas Gage and what it tells us about human functioning and the human brain. Expect a question on this on your quiz and on your test. But I think you'll find it very interesting, so do go there. It's amazing that he survived the accident in a day and age where he had no EEGs, CAT scans, PET scans, MRIs, no antibiotics, and yet he survived, though as you saw, distinctly worse for the wear. So let's consider the left and right hemispheres, in other words, the left and right sides of the brain. Our brain is lateralized, meaning each side has slightly different functions. The left is a logical side. If you're into Star Trek, it's the Mr. Spock side. It also prefers linear thinking. Linear means sequential. Perhaps you're in algebra right now, or have had it, or will have to take it. It's often called linear algebra. You've got to do the order of operations in the correct order, otherwise you will not get to the correct answer. Or reading is linear. You can't read the words in any order. John hit Jane is very different than Jane hit John. Order matters. It's linear. Language, as we saw earlier, the left temporal and left frontal lobes are our language lobes. Let's consider the right side. It is the emotional side, particularly the darker emotions. It's the Dr. McCoy side, if you don't mind the analogy. It is not a linear thinker. It is holistic. It likes the big picture. That's what holistic means. Spatial skills it likes too. Spatial has to do with distance, design, and layout. So example, drawing is spatial. Reading a map or drawing a map is spatial. Writing is spatial. Visualizing how they get from here to there is spatial. So again, spatial is distance, design, layout. Now, as you take your notes, right in the middle of the page, each side of the brain controls which side of the body? Same or opposite? Opposite. So let's say that you go to the hospital to visit your great Uncle Harry. And let's say great Uncle Harry's had a stroke and he cannot use his right hand, and the right side of his face is drooping. Where did the stroke occur? Well, clearly on the left side of the brain. Since he can't use his hand, we know motor cortex is involved. That would be definitely including the frontal lobe. Let's say that you also visit your Aunt Harriet, who also had a stroke, who detests your Uncle Harry. Aunt Harriet, when you come into the room, her eyes beam and she's happy, but she cannot talk with you, though she clearly understands. Which side of the brain? Well, it would be the language side. So clearly her stroke included the left frontal or temporal. I didn't give you enough information to be able to tell which one, but definitely a left side injury to the brain. And you'll be as accurate as an MRI in terms of this. Now let's next consider what connects these two sides. Your left side and your right side are connected by wiring. Really parts of the neuron. Would wiring be the dendrites, the soma, or the axon? Axon. So the corpus callosum is really a bundle of axons connecting both sides. This bundle of axons is formally called the corpus callosum. So we have one big brain because the left and right sides are in constant communication. Again, we have one functional brain. If we didn't have the corpus callosum, we would not have this single brain. On the next slide, we'll consider people that do not have one functional brain. A very tiny percentage of people are born without a corpus callosum. Last semester, for the first time, a student shared with me that she was born without a corpus callosum. Other people have had their corpus callosum surgically severed. Consider the two blanks in the slide. Clearly, the first blank would be corpus callosum. Do you know why we would do such a drastic surgery? You might remember from your text, it's for severe, severe cases of epilepsy, though almost always epilepsy is well treated by medication alone. After this corpus callosum is severed, this person has not one brain, but two separate brains, each with its own separate consciousness, a true multiple personality. It has surprising little effect other than it greatly improves their epilepsy condition. It's not like one lobe will go to the movies and the other one will go to class. They're always with each other processing the same information. So surprisingly little effect. Though I did read a case study in the person's one oddity is, when you get up in the morning, you go to your wardrobe, you decide what you're going to wear. One hand will reach for one outfit, another hand will reach for a different outfit. Each side of the brain was in a different mood, wanted to wear a different outfit, and neither wanted to, give up, relinquish. So sometimes one hand would slap the other as the sides of the brain tried to figure out who was going to win. But other than that one condition, they lived a very, very normal life and greatly improved. Some of these split brain people have volunteered to be in studies. So the slide, which we said the left side of the brain does this, the right side of the brain does that, a great percentage of that research came from studying these split brain people. So consider the slide. This is one person sitting with a screen that they cannot see through, being asked to determine what they're feeling. This person in the left-hand side cannot say ball, cannot verbally identify it. On the right side, in this different circumstance, they are feeling that ball and they say ball. See if you can understand this slide. It all has to do with lateralization. In the first image on the left hand sends its information to the right side of the brain, which has no language. So that side of the brain can feel the ball, but cannot verbally say it. If you gave it a picture, it could point to the ball. If you lifted up the slide, it would point to the ball, but the right side does not have language. Now in the right-hand picture, the right hand is giving information to the left side of the brain, and vice versa. The left side of the brain is the language side, so it not only knows it's a ball, in that circumstance, he can say ball. So it all has to do with the functions, the lateralization of each side of the brain. Let's relate our topic to the slide. Dolphins are mammals. They need to breathe air, but they also have to sleep. There's no Coeli Posturepedic floating on the surface. So how do they manage to swim and breathe all night without drowning? Think about it for a moment and relate it to our topic. And be impressed if you actually guess. The answer is the dolphin has a natural split brain. So at night, one side is fully awake and the other side goes to sleep. And later on, they switch. So it can, with will, decide which or both sides will be active, hence its survival. Fairly impressive, I would think. I often wonder if dolphins like the different personalities of each side better. Maybe on, I don't know, Hillary, you like her left hemisphere, but you find her right hemisphere very annoying. I don't know, but clearly very interesting, unnatural split brain situation. So we've considered the cerebral cortex and the four lobes. We've considered the corpus callosum. Let's consider other critical brain structures. Let's start with cerebellum. You have two cerebellums. They're the balls at the base of the brain. Their job? Coordination of movement. I often ask my students, can your cerebellum get drunk? Well, of course it can. What would be some signs that you have a drunken cerebellum? Maybe slurring your speech because your lip and tongue cannot coordinate. Maybe staggering, your legs are not coordinating. Maybe you reach for your drink and knock it over, hand-eye, coordination. So cerebellum coordinates movement. Pons, in Latin, pons means bridge. It bridges two structures. Which two structures? Well, the two balls, so you can be coordinated. It is also essential for sleep. There's a famous, very sad case study. This gentleman could not get to sleep for a couple days. He went to the hospital, they did brain imaging. For some unknown reason, his pons had massive damage. He could not get to sleep. He lapsed into a coma and died because we must sleep to live, and you must have a pons to sleep. And sadly, he did not have a functional pons. Next, let's consider the medulla. Though if you're feeling very fancy, it might be the medulla oblongata. The medulla controls vital functions like breathing, that's pretty vital, heart rate, pretty vital, temperature, and so on. So vital functions. We do not ever operate on the medulla because it's not possible. It cannot be interrupted. It cannot be damaged. Next, let's consider the hippocampus. Its job is to form memories. There's a very famous case study. This individual had seizure after seizure after seizure every day. He had no quality of life, and his very life itself was being threatened by these constant seizures. The short circuit in his particular condition happened to be in the hippocampus. With no choice, surgeons removed his hippocampus, the former of memories, in other words. After the surgery, his memory of the past was fine because those memories were fully formed, but his ability to form a new memory, in other words, to learn, virtually totally destroyed. Imagine going the rest of your life and never learning one new thing. So he could read the same newspaper every day for the rest of his life. If he met a nurse after his surgery, every time he saw her, or even after lunch, the same conversation. Hi, what's your name? Where do you go to school? Do you live locally? Do you have kids? And so on. So not able to learn new things. An odd life, to be sure. Next, let's consider the thalamus. It is your sensory relay center. All the senses will, except for one, send their information through the thalamus. Can you think of some examples of these senses? So your eyes send information through. Your tongue sensory cells send information through. Your skin receptors send information through. The one exception, sense of smell, it does not use the thalamus. Lastly in our list, under the thalamus, quite literally, hypo meaning under, hypothalamus. This controls our instinctual drives. Now, way back when I took intro psych, Dr. Guzzi told us, remember the 4 F's. It'll help you remember the major drives. I did, and I still do. It regulates the drives, such as eating behavior, but let's say feeding, that'll give us an F. Consider an animal that's cornered. Well, it can behave aggressively, but let's use fight to make it an F. But sometimes, whether it's a person or a nation, it's better to put your tail between your legs and run away. So you can say fleeing or flight as the third. And the fourth, well, mating. That's it. I'm not going to say it with an F, but I think you can think of mating and spell it with an F pretty easily, yes? So fight, feeding, flight or fleeing, and mating, spelled with an F. On the bottom, before we go on, go ahead and use that as a review. So I wouldn't barrel through these PowerPoints. I would do a chunk, study to your good, do another chunk, review, study, do another chunk, review, and study. So you should be learning as you go away. Don't plan to learn this all on the weekend of a test. It will not be good for you or me. So definitely test yourself and learn as you go along the way. Conjoined twins are very rare. Those joined at the head, the rarest of all. Very few survive. Tatiana and Krista are unique. They share a thalamus. Think of what the thalamus does and think what it could mean to them. Please watch the video. I think you'll find it very interesting, and I would suggest that you pay attention to what they share because you could easily see a question on that on your quiz and perhaps your test. Hint, hint. Now let's look at high-tech diagnosis and treatment. 2 new symbols for you, perhaps. The next time you get a prescription, if it's a paper one, look on it, you'll see a big RX. That's the abbreviation for treatment. In class, if we were face-to-face, I would ask people to share their experiences, and many people have had one of these or more of these. Perhaps that would be you. Let's consider the EEG, electroencephalograph. Do you need to know what it stands for? Yes, but if you break it down, it's not bad. Electro, as in the brain's electricity, as in the action potentials. Encephalo, can you think of any medical terms with encephalo? Like encephalitis? It means head or brain. And graph is to measure, to show a graph, like at the bottom of the slide. So it's basically a graphing of the brain's electricity. So if you break it down, really not bad. Electrodes are attached to the scalp using a very sticky glue. If you're thinking about getting a short haircut or a buzz cut, the time to do it is before you have this particular procedure. Or it can be applied in a bathing hoop embedded sort of apparatus with electrodes on it. Below you see the EEG pattern. Why is it used? A few very common reasons. To diagnose epilepsy, they'll hook you up and try to induce a seizure to see where the difficulty lies. It could be for sleep issue diagnosis or to determine brain death. So EEG has various medical uses, those three being amongst the very most prominent. Now let's consider more modern technology. The EEG dates back to the late 30s. Let's now consider the CAT scan, which is often called the CT scan. It's an older technology, dates to the early 1970s. I assume many of my students have already had this particular examination technique or will have it later on in life. It may or may not require dye. Dye could be the drinkable type, the type that might be injected directly into a joint or sometimes an IV. The person is in the machine, as you see below. Students sometimes don't know if they had a CAT or an MRI. I tell them you can tell by the amount of sound it made. If it made a gentle whir-wish noise, it's a CAT scan. If it was very loud and clanking, MRI. The picture on the right is the basic picture, though the C in the CAT scan is for computer, so the computer can be used to generate a more interesting and easier to read picture. Here's a little CAT scan humor for you. I always inquire, do I have any true house fans in my class? If anybody raised their hands, I asked them, what would house say about the slide? And sometimes students do get it right. House would say, it's never lupus. About every other show you would say, it's never lupus. So that was a test. A little more CAT scan humor. Presumably the only time this CAT scan will actually scan a cat. It's silly, but I ask my students to say it as quickly as they can with me aloud. It's stupid, but it's also fun. Let's now consider the MRI. The M is for magnetic. The person is placed in a very strong magnetic field, and radio waves are directed at them. The energy that the person emits is measured by computer, which generates a picture like the one shown on the left. The MRI is quite loud. It will clank and clunk. You'll often be offered earphones and offered to select a radio station. Don't go with talk radio. I did that. You can't hear talk radio. Go something with a good driving beat. Because you're placed in a magnetic field, what sort of questions do you think they might ask you? Well, do you have any metallic or artificial implants? Do you have body art, piercings? The nature of your tattoos, such as prison tattoos and so on, because the metal in the body could be made very hot or be pulled from the body. So those are concerns. There's a newer version. The MRI itself dates to the late 70s, but a newer, much fancier version is called the fMRI. F is for functional. The fMRI dates to 1990. In the PET scan, the person is given an IV with radioactive glucose. Since glucose is the fuel of all our body cells, as they burn glucose, they become radioactive, and you become radioactive. That can be detected by the use of technology and portrayed on a computer screen, such as in the image below. It's not very frequently used. If it's used, it's most commonly done for research or for cancer detection. I've only had a handful of students who have known somebody that had a PET scan, and it has always been for cancer detection purposes. So we mentioned some of the most commonly used methods of diagnosis, DDX. Now let's consider some of the high-tech treatments available, starting with VNS, in other words, vagus nerve stimulation. This is an uncommon treatment. It's a fallback position for depression and epilepsy. The electrical supply, the battery, is often implanted underneath the collarbone. Wiring under the skin leads to the vagus nerve into the neck, and it gives it gentle pulses. And these gentle pulses will help to diminish depression or to extremely decrease the prevalence of the epileptic seizures. So not a common treatment, but good for those people who are in need. Let's consider TMS, transcranial magnetic stimulation. The person's put into a very strong magnetic field, which is very specific. It's a very limited area, and it's got to be very close to the surface of the brain. This is a newer technology, just over 10 years old. It is FDA approved for a few purposes, and as time passes, I'm sure we'll see more. It's used to treat depression, Parkinson's, migraines, and tinnitus. So keep in the back of your mind if you know somebody that suffers from migraines or severe ear ringing, or perhaps you'll develop an issue. It's not remotely a comfortable procedure. I read an author who just compared it to having a jackhammer put onto your skull. Not pleasant. Clearly this woman has a slight smile. She is not getting TMS. But it can make all the difference in the world for some people. It's a fallback position, and perhaps in the future it'll be less uncomfortable. But for those who need it, it could be life-saving. DBS is another one of the newer stimulation techniques. It stands for deep brain stimulation. It's just a little over 20 years old. It's used to treat various things. The FDA has approved for Parkinson's treatment, depression, and chronic pain. It is not a common treatment. I have never come across anybody personally who's had it. A friend of a friend just had the first of 2 surgeries a couple days ago. The battery is implanted under the collarbone or apparently in the armpit. Wiring will lead to the battery underneath the skin, underneath the scalp, to an electrode that's been implanted in the brain, and there will be gentle stimulation, which might diminish Parkinson's symptoms or depression, or help the person with chronic pain. Again, not at all common, but for those people who need it, it will be a lifesaver. We're on our last slide of new content for this very long, but hopefully interesting chapter. The last slide looks at brain protections. Obviously we have our skull. I'm not going to say anything more on that. Let's consider ventricles. Let's say that you hear 2 biology students talking in the hallway about ventricles. What are they probably talking about? Most students say heart. And what's the ventricle in a heart? Well, it's a fluid-filled chamber. So what do you think a ventricle will be for our class? Hopefully an easy question. A fluid-filled chamber. A ventricle is always a ventricle. And you can see in the picture the brain's ventricle. The brain's ventricle, at least one of them, makes our cerebral spinal fluid. So if you've had the joy of painkiller being put in, perhaps an epidural, or fluid taken out to check for, say, meningitis or encephalitis, that cerebral spinal fluid actually began in the ventricle and eventually filtered down to the spinal canal. The ventricles also make the fluid the brain is floating in. The brain is surrounded by fluid, just as a fetus is surrounded by fluid. Well, the brain is also surrounded by fluid. It's an additional protection. If you're ever in a car accident and they look in your ears or nose, they're looking for cerebral spinal fluid. Hopefully they don't see any. Let's consider the blood-brain barrier. It has a BBB theme. To keep with that, I'll have you think of it as perhaps the Brita water filter of the brain. In other words, it's a filter. It protects the brain by filtering the blood supply, keeping out some harmful materials. Unfortunately, although this is a very good thing, if you have a brain condition, that makes treating it very difficult. Not only do they have to find the magical drug that works on your brain condition, chemically, that drug's got to be able to fit through the blood-brain barrier. So many things that work wonderfully in a petri dish in a laboratory don't have practical uses because they can't get through this barrier. The last term is the meninges. What word does that remind you of? Probably meningitis. What is itis? A swelling or an inflammation. Can you think of some words with itis? Laryngitis, appendicitis, bursitis. Many terms indicate swelling of the tissue. Meningitis would be a swelling of the meninges. I always ask to see if anybody knows anybody that had meningitis. I always ask that really tentatively because not everybody that has it will survive it. So it can be nothing more than a bad bout to something that leads to permanent damage, such as blindness if the occipital lobes are involved. What about the temporal lobes if they're involved? Perhaps deafness. What about if the spinal cord is involved? Well, maybe paralysis. or it can permanently affect the level of consciousness. It can also cause death, particularly if the medulla is interrupted. So the meninges, a three-part protection surrounding the brain and spinal cord. So in meningitis, that three-part protection swells, putting pressure on the brain and spinal cord, causing the damage that's often associated with this disorder. So again, meninges, three-part protection. And with that, we're done with the new content. There are some review slides that you might find very helpful in your studying, but of the new content, we are now done. I hope you found this chapter as interesting as I do. After you've completed this chapter and found time to study it, please go and actually do this little assessment. You'll get much more out of it than just writing down the names on a slide that you might have printed. So let's see how you did. For memory formation, that would be the hippocampus. Hopefully you remember the mnemonic. Connects the two balls, key to sleeping, that'd be the pons. The four F's, that would be the hypothalamus. Sensory relay center, thalamus. Brainstem, key for vital functions, that would be your medulla or medulla oblongata if you're feeling fancy today. The two balls, key to the coordination of movement, that would be your cerebellum. Divided into four lobes, that would be the brain's cerebral cortex. And the structure that connects the two halves of the brain, that would be your corpus callosum. Hopefully you've done well so far. Let's see how you did on the bottom. Connecting the two hemispheres, that would be your corpus callosum. What are the four units of the hemispheres? It would be the four lobes. Which one is for hearing? Well, it allows us to hear tempos, and it's by our ears, and it has our language centers, our oral centers, so that would be your temporal lobes. For social skills and planning, remember Phineas Gage, he lost his social skills dramatically after his accident. That'd be the frontal lobe. Which one is for vision? Is it optical or occipital? Hopefully you went with occipital. For body senses, was it parental or parietal? Hopefully you went with parietal. Which two are for language? Well, it'd be the frontal and the temporal. Which side? For just about everybody, it would be the left. So again, it'll be much more effective if you, after you study, use this to provide you feedback rather than just jotting down the correct answers. So the major inhibitory neurotransmitter, that would be GABA, GABA. Next one, major excitatory neurotransmitter, that would be glutamate. Next one, the natural, or in other words, endogenous painkiller, that would be endorphins. For pleasure, or related to both schizophrenia and Parkinson's, that would be dopamine. Mood and mood disorders, particularly both norepinephrine and serotonin, and the one below it, also norepinephrine or serotonin. And last one, particularly involved in memory and especially Alzheimer's, that would be acetylcholine. Next, as always, I'd ask you to go ahead and, after you've studied, fill it in on your own. It'll give you important feedback in terms of which parts of the chapter you need to work more on to achieve a satisfactory level of understanding and hopefully performance on your test. So starting on the left, central nervous system. That's the parts of our nervous system encased in bone, which would be your brain and spinal cord. On the right, we're going to look at your peripheral nervous system. It's on the periphery, in other words, on the outskirts, on the outside of bone. So peripheral nervous system. We have the motor pathways, which can be voluntary. That would be allowing us to move our body and feel our body. That would be somatic. And involuntary, that would be not automatic, but the word is autonomic, a branch for speeding it up associated with stress and emergencies. If you remember your mnemonic, the sympathetic is the emergency associated branch. And the opposite, the one for resting and relaxation, that would be parasympathetic. So you should place the hypothalamus and the pituitary in the brain. Pineal, which we haven't spoke of yet, but if you did try it, that would also be in the brain. A testicle, I assume that's obvious. Ovary, somewhat above the testicles in the abdominal cavity at left and right side. Pancreas, towards the middle. Thyroid, looks like a bow tie, so put it on the neck. Thymus, we will skip in this class, and the adrenal glands. If you drew in a kidney on both the left and right side, place it sitting on top of the kidney. So the myelin sheath that we associate with MS, that would be the insulation of the axon, so it would be shown in pink here. Synaptic knobs would be the little knob-like, button-like structures, which really aren't shown in this particular diagram. They should be knob-like or button-like at the smaller end, the end that does not have the nucleus inside the cell body. Synapse, microscopic spaces between cell. So maybe where the one axon is reaching out to the two cell bodies, that'd be a good place to write a synapse in the center. Dendrites, tree-like and branching. That would be on the end that's bigger, the end that has the soma, the end that has that, you can see the nucleus inside. Axon, the cable, going from the cell body to the branching. And last one, soma, would be the large cell body shown in yellow. This particular diagram does show the nucleus inside each one, although we didn't speak about them in class. So the diagnostic tool that's used is the X-ray. That would be the CT/CAT scan. The diagnostic tool, which uses radio waves and a magnetic field. M is for MRI, quite literally in this example. The next one, the treatment, very, very rarely used, deep brain stimulation, in which an electrode is actually permanently left in the brain. That would be DBS. Next, for diagnosis, be the EEG, electroencephalograph, shows brainwaves. And lastly, a rather new kid on the block, for treatment, TMS, transcranial magnetic stimulation.